This section we're going to talk a lot about just counting, and it seems kind of silly, but it's basically when we have a ton of different events going on and different experiments that are performed together, how can we figure out how many ways we can do that? We'll talk about if we need to form committees and things like that. How many ways can we form that committee if we need to pick so many people from a group? If you have a race, how many ways or combinations can you pick a first and second place position? So we'll talk a lot about just how we go about counting that. And there's two main ways with permutations and combinations. So we'll talk about that, and then we'll also utilize this counting method to be able to find probabilities. So to start out, we're going to start out with what's known as the counting principle. And basically what that means is if you're doing multiple events together and you're doing one after the other, you're going to just multiply the number of ways you can do each to figure out how many ways you can do both experiments together. So if an experiment can be performed in C distinct ways, and then a second experiment can be performed in D distinct ways, then the two experiments can be performed in C times D distinct ways. So I'm going to show you this with an example that we can actually write the full sample space for. But you'll see later on, it's not something you can actually write the full sample space of, but you'll see why this works. So suppose we flip a coin and then we toss a fair six-sided die. We want to figure out what that sample space is. So if I look at the coin, there are two different outcomes for that. The coin is going to land on heads or it's going to land on tails. When we roll that die, there are 6 outcomes. You can get any of the numbers 1 through 6. Okay. So there's 2 outcomes for the first event, 6 outcomes for the second. So if I'm going to do both of these events in total, there are 2 times 6 or 12 outcomes for these 2 experiments. Okay. So again, listing 12, not bad, but say there were going to be 752 outcomes, a lot harder to list them all out. So just to show you that there are indeed 12, we're going to go through and look at our sample space. So first possibility is you get a heads when you toss or flip the coin and a 1 when you roll the die. Well, to keep things consistent, I'm going to run through every possibility with that heads. You can also get a heads followed by 2, a head followed by 3, heads, then 4, heads, then 5, and then heads and 6. So you can see there are 6 ways here. Well, now I can run through the same thing, but assume I got a tails when I flip the coin. So tails and then a 1, tails and a 2, tails and 3, tails and 4, tails and 5, and tails and 6. So indeed, there are 12 different outcomes for this sample space, which we got just by multiplying the number of outcomes together. Okay. So let's try a harder example. And again, this extends if you have 3, 4, 5, 6, 7 experiments. You just multiply the number of ways to do each of them together. So say you decide to enroll in 4 classes this next semester. You're going to take a sociology class, a chemistry class, economics, and humanities. And then when you go to sign up, there are 7 sociology classes, 4 chemistry, 3 economics, and 4 humanities classes that ultimately fit your schedule. You want to figure out how many different ways can you select your classes. So again, lots and lots and lots of possibilities. So what I tend to like to do for these is I kind of like to make a little chart. I'm going to select 4 things, so I'm going to make 4 bars for each of them. I have 7 sociology classes. I have 4 chemistry classes, 3 economics, and 4 humanities. And all I'm going to do then to figure out the total number of events is multiply them. So 7 times 4 times 3 times 4, which gives me 336. So ultimately, there are 336 ways to pick our schedule. So a lot of options for that, okay? So again, you just have to figure out how many ways can that specific event happen, and then you're gonna go ahead and multiply them all together. So let's try another example. A password must consist of 2 lowercase letters followed by 4 digits. We're gonna determine the number of passwords possible if repetition is allowed, okay? So if you think about the 2 lowercase letters, there are 26 of them. If it could have been lowercase or uppercase, then you really have 52 because you have 2 options for each. And then there actually are 10 digits. So if you think of a keypad, you have the numbers 0, 1, 2, 3, all the way up to 9. So 1 through 9 is 9, and then you add that 0 in. So that gives you 10 digits in total. And again, I'm going to lay out a map for what this looks like, because there are specific rules for this password. They tell us that it's going to be 2 lowercase letters, so these have to be letters, followed by 4 digits. And then they tell us that repetition is allowed. So in the first piece, I have 26 options for each of these letters. So each letter has 26 choices. And then for the digits, again, I have repetition, so I have 10 options for each of them. So when I go to find this total number, I'm just going to multiply these together. So there are 26 times 26 times 10 times 10 times 10 times 10, which leads to 6,760,000 possible passwords. Which is a lot of passwords with just a small amount of digits, okay? Now, if I change this slightly and I say repetition is not allowed, what that's basically going to do is affect these positions, because once I pick a letter, I now have less options for the remaining. So if repetition is not allowed, I'm going to go ahead and cheat because the password itself does not change. I still have 26 options for the first letter, but once I've picked that, I now have 25 options for the next letter. So there's 1 less letter to choose from. Likewise, for the first digit, I have 10 options, but once I've put that digit, I now have 9 for the second spot. Once I pick that digit, I've got 8 for this spot. And then again, once I pick that digit, it's thrown out. So I have 7 remaining for that last choice. So each time there's 1 less digit. So in total, there are 26 times 25 times 10 times 9 times 8 times 7, which is 3,276,000 possible passwords. So you can see when we changed that to not allow repetition, it actually ended up cutting our options in less than half. So we have a lot less possibilities there, okay? So in these two particular situations, we were told that order of letters and numbers. But if you think of your other passwords, they don't tell you that you have to start with a letter versus a digit. You also get to throw character options in there. So in this case, I might be able to also rearrange the order. So not only do I have these options for every single placeholder, but I could start with a digit, then a letter, and then all digits. Or I can do a letter here, a letter at the end, and then replace this with a digit. You can rearrange these, okay? So in this case, the order is going to matter, okay? So what we can also do is we can figure out the number of ways we can arrange the letters and digits. And this is the concept of a permutation. So a permutation is any ordered arrangement of a given set of objects. So this is going to be the key difference between the two things we're going to talk about. One, order is going to matter. The second, the order is not, okay? So we're going to come up with a way that we can actually evaluate this. But what we're going to do first is just work with an example that's a little bit easier. And then we'll introduce a concept that is very unique to counting, which is called factorials. So to start out, we're going to look at a couple different objects. We're going to determine the number of ways we can arrange the following pictures. So we've got a smiley face, a cloud, and then we've got the Deathly Hallows symbol, if any of you like Harry Potter. So I tried to pick things that were relatively easy for me to draw, but this order is going to be our first arrangement. My second order, what I'm going to do is I'm going to kind of copy and paste these each time because it would take me way too long to go ahead and draw them every time. Maybe we keep the smiley face in the same position, but we go ahead and switch the order of the cloud and the Deathly Hallows symbol. Then my third option is maybe I don't keep the smiley face in front. Let's go ahead and put the cloud in front. And then likewise, if I go to do a fourth arrangement, I can keep the cloud in the front, but switch the order of these two. For my fifth option, now I'm going to go ahead and put the last symbol that hasn't gone in front. And then we'll go ahead and put the smiley face followed by the cloud. Oh. And then one final instance, we keep the same thing in the starting position, but then we go ahead and rearrange these two. And so again, this would work with any three pictures that you choose, or really any three objects. They don't even have to be pictures. They can be cups, they can be plates, they can be backpacks, whatever you can think of. And they could be totally different things. But if I have three objects, there are going to be 6 ways to arrange it. One object gets to stay in front, you flip-flop the other two. Put a new one in front, flip-flop the other two. So in general, there are going to be 6 ways to arrange the 3 pictures. So really what I could have done is I could have used these placeholders. You have 3 objects here. In that first position, you have 3 possibilities for that first picture. Once you place that picture down, you now have 2 to choose from for the second position. And then once you place that second picture, there is a single one left for the third spot. So applying that counting principle, we go ahead and just multiply these. 3 times 2 times 1 ends up giving us 6 ways to arrange 3 objects. So this is exactly how many permutations there are for 3 objects. If there are 4 objects, well then you'd have just one more in front here, which would be 4 times this. So what ends up happening is you're going to see this a lot where you start with a number and then you keep multiplying down until you reach 1. This is actually something called a factorial. So the number of permutations of n distinct items is n factorial, and it's denoted with an exclamation point. So what you do is you start with whatever integer you're given. So in this case, just to kind of go back up here, this is really 3 factorial. That gives us 6. Number of ways to arrange 3 objects is 3 factorial. You start with that integer, and then you keep going down until you reach 1. Okay? So the order and the arrangement is going to matter. So these two resulted in 2 different things, even though they're the same objects. Okay. So just to get used to these factorials, let's go ahead and practice just evaluating some of them. And we're actually going to see some of the nice properties that happen with this. So if I look at 3 factorial, that means I'm going to start at 3, and I'm going to keep multiplying until I get down to 1. So I keep decreasing. So 3 times 2 times 1 gives me 6. If I look at 4 factorial, I start at 4 and I keep decreasing down. 4 times 3 is 12, times 2 is 24, times 1 still gives me 24. The other thing that ends up happening, if you look in here, this is 3 times 2 times 1. That's exactly 3 factorial. So one thing you can actually always do is if I start with 4 factorial, I can pick off the first number, and then I'm going to get the next integer factorial down. Okay. Likewise, if I look at 5 factorial, that means start at 5. 5 times 4 times 3 times 2 times 1. This will end up giving us 120. But again, if I look at 4 times 3 times 2 times 1, that's exactly 4 factorial. So what I can say is if I have 5 factorial, I can pick off the 5, and I'm left with the next integer factorial. And then really you can keep doing this process. I can pick off the 4 and I'm left with the next integer factorial. I could pick off the 3 and I'm left with the next integer factorial. So it's a nice property that you have, which works great when we have to simplify things, okay? And then just kind of as a side note, because this will pop up a little bit later, this is telling you the number of ways to arrange that many objects. So there are 120 ways you can arrange 5 objects. There are 24 ways to arrange 4 objects. So if I look at 0 factorial, this is the number of ways to arrange 0 objects. This is actually 1. There's one way to do it. There's nothing to arrange. So this is because there is one way to arrange 0 objects. So it's something that's just kind of a definition that fits in, okay? So we're going to try a couple examples first, and then this will lead into if we have a larger group and we're selecting so many individuals, how many ways can we do that? So starting out, 7 pictures are to be hung on a wall. How many ways can they be arranged from left to right? So again, if you think you're lining up 7 family photos, the order is going to matter here. Because if I put the picture of myself first versus at the end, it's a different way to arrange it. So this is something I want to try to point out when we can, but notice the order of the picture matters. So there are 7 objects. So if I want to arrange those 7 pictures, there are 7 factorial, which is 5,040 ways to arrange the pictures. Okay. So if you have a handheld scientific calculator, you should see that there is that exclamation point for factorial buttons. Unfortunately, your phones tend to not have them. It just depends on the type that you have. If you're using an iPhone, there is a way to put it in scientific mode so that you can see the factorial button, but it's really just dependent on it. I would definitely recommend getting a handheld calculator though to be able to use during tests and everything. So this way you're comfortable with it. Just to show you on this calculator, there is a button here for it. So let's go ahead and clear that. If I want 7 factorial, I do 7 factorial, and you can see that gives you the 5,040. So 5,040 ways to arrange the 7 pictures, okay? So let's try another example. We were told there are 9 people in math club. Collectively, you decide to put each person's name in a hat, and you're randomly going to select a president, vice president, and secretary. We want to figure out how many ways can we possibly do that. So this case, the order does matter because the first person that's picked out of the hat is going to be the president. Second person picked out of the hat, vice president. Third person, secretary. So the position matters because you're going to get, or the order matters because you're going to get a different position for the club based on that, okay? So I have 3 names that I'm picking out. Starting with our president, if I pull in that bag, there are 9 people in there to start with. So I have 9 possible ways to pick that president. Once that person's picked, though, they no longer can have another position. So when I move on to the vice president, there are only 8 names remaining in the hat. And then when I move on to the secretary, 2 people have already been put in positions. So there are 7 people remaining for the secretary. Okay. So using that counting principle, we just go ahead and multiply these together. And 9 times 8 times 7 gives us 504 possible outcomes. Okay. If instead I was just picking to form a committee, that's a little bit different because the order is not going to matter. Whether you're the first person for the committee or not, or the third person for the committee, it's not going to make a difference. So the order is not going to be as significant, and there are going to be less outcomes as a result of that. So this is actually a really common process that we're going to see really frequently. So there's actually a way we can calculate this based on the number of people we had and the number of people we were selecting from this. So what I'm going to do is actually build where this comes from. So notice we ended up with 9 times 8 times 7 as our final answer for picking 3 people out of 9 where the order mattered. Well, what I can always do is multiply top and bottom by the same thing. So what if I see that 9 times 8 times 7, that looks like the start of factorials. What if I go ahead and fill in the rest of the pieces? So we need 6, 5, 4, 3, 2, and 1. But if I'm adding them in the top, you've got to multiply by that in the bottom as well. So really what you have in the numerator is 9 times 8 all the way down to 1. That's 9 factorial. And that's how many people were in the club. And in the bottom, you have 6 factorial. Now, that doesn't seem like it fits. However, it does come from the fact that we're picking 3 individuals. So if you notice, this number plus 3 results in the total number in the club. So really, the way we can represent this is 9 factorial over 9 minus 3 factorial. So this is the number of people in the club and in the bottom, this was the number of people minus the number we selected. So we chose 3 and the order did matter. So this is a nice example because we can see where this comes from. But now say I had 1,000 people and I'm going to select 52 of them. I don't want to go ahead and make 52 lines and try to figure out and keep track of everything and multiply it nicely. But it's going to result actually in the same kind of formula. So I would have 1,000 factorial. And then from those 1,000, I'm picking 52. So I would do 1,000 minus 52 factorial in the bottom. So in general, the number of permutations possible when R objects are selected from N objects is given by the following. So permutations, again, order matters. So the way we represent this is we say P for permutations. From N objects, we're arranging R. So the formula for this is we're going to have the number of objects factorial in the top, and then the number of objects minus how many we're selecting in the bottom. So again, you can think of this as from N objects, we're arranging R. So order matters here, okay? If order doesn't matter, then you're going to see that's something that's called a combination. Now, unfortunately, your scientific calculators, again, are going to have a button for this, but your cell phone is not. So definitely get a handheld calculator. If you need help finding this button, just let me know. It just depends on the kind of calculator that you have. But even my one that I have on here does not have that button. So unfortunately, what I'm gonna do in these videos is I'm just gonna go ahead and kind of write everything out, and I'll show you how it's simplified. But again, you'll have to go through and figure out how to use your specific calculator on your own. But again, ask me if you have questions on it. I'm typically good with all of that. So let's try an example of this. We're gonna do it 2 different ways. A teacher has 10 students and she will select 4 to win a prize. If each prize is different, how many ways can the prizes be awarded? So again, I'm going to go ahead and draw those 4 little lines to represent those 4 prizes. Because this one's, I think, a little bit easier using the counting method, but I'm going to show you this is really a permutation as well. So from 10 objects, we're arranging 4 because the arranging gives a different object to a different kit. So for my first possibility, I have 10 students that I can pick to give prize 1 to. Once that student has a prize, we then have 9 that could get prize 2. That student gets a prize, you have 8 left. And then that 4th and final student, you have 7 different ones to pick from to give prize 4. So multiplying these together, 10 times 9 times 8 times 7 gives us 5,040 ways that we could distribute these 4 prizes to the 10 different students. Or again, the order does matter because if I switch the order, a different kid gets a different prize. So from 10 objects, we're permuting 4 of them. So using our formula, we do 10 factorial in the top, and then in the bottom, we have 10 minus 4 factorial. So from 10 objects, we're permuting 4. Well, on the top, can't do anything with that yet, but 10 minus 4 gives us 6 factorial in the bottom. So to simplify this, you definitely could do 10 times 9 times 8, all of that in your calculator. However, remembering our rules, we can pick off the first number and get the next number factorial. So if I pick off the 10, I'd be left with 9 factorial. But I can do that again, and I'm left with 8 factorial. And then I can do it again, and I'm left with 7 factorial. And if I do that one more time, I'm left with 6 factorial. And I like that because the denominator is also 6 factorial. So these end up canceling each other out, and you see we still get the 10 times 9 times 8 times 7, which leads to 5,040 ways to arrange those prizes. So now we're going to consider what happens if the order does not matter. So again, if these were all the same prize, it wouldn't make a difference which kid got which particular one because they'd all end up with the same thing. And this is going to be when we have a combination. So a combination is a distinct group or set of objects without regard to their arrangement. So the order does not matter. So before we try to evaluate these, let's start with some situations and figure out, is it a permutation or is it a combination? So in the first scenario, you're going to adopt 2 dogs from a shelter with 10 dogs. Well, if you think about that, the order you adopt them in doesn't matter because you're still selecting 2 dogs. Which one you pick first, which one you pick second, doesn't matter. They're both yours. So the order does not matter. Because of that, this would be a combination. So ultimately, there are going to be less ways to pick 2 from the 10 because dog 1 and dog 2 is the same as going dog 2, dog 1. You still end up with both of them. If we look at part B, you're arranging 10 books on a shelf. Well, here, the book you put in the first spot is going to be very different than the book you put in the last spot. So the order does matter. So this is a permutation. And in this case, if you're arranging all 10 and you want the number of ways to do that, we know it's 10 factorial, but also it fits into that formula we have up here. From 10, you're choosing 10. So in the bottom, you'd end up with 0 factorial, and 0 factorial is 1. Okay. So again, we want to get to a formula for this. However, I want to start with an example to see, can we build it, or can we see that, yes, this formula does mash up nicely. So we're going to look at a committee. 2 people are going to be selected from a club of 4 to form a committee. We want to figure out how many different ways can that order or can that committee be formed. So again, it doesn't matter which person gets put in the committee first. No one has a hierarchical role. So the order selected does not matter. So what I'm going to do is I'm actually going to list out all of our possible committees because I picked a small number to show you that. Let's call our members A, B, C, and D, the 4 people in our committee. I'm going to look at the first member that I select, and then I'm going to go ahead and find the second member we can pair them up with. So starting with person A, well, I can pair them up with everyone else. So we can have A and B as a committee, A and C as a committee, and A and D as a committee. Well, then maybe I select person B to begin with. I don't, however, want to put A here because that's exactly the same committee. Instead, I want to pair person B up with people I haven't paired him up with yet. So he hasn't been paired up with person C or with person D. Then if I move on to person C, again, I've already paired C with A and B, so the only new pairing I can get from here is D. And then when I get down to D, well, I've paired D with C, I've paired D with B, and I've paired D with A. So there are no new committees that can be formed here. So in total, if I look at my number of connections, I have 1, 2, 3, 4, 5, 6 committees that can be formed. So really, the number of combinations possible when R objects are selected from N objects is given by the following. So to say combination, we use a C. From N objects, we're selecting R. So again, you'll see this button on most of your calculators. The other way you'll often see this is with parentheses. In the top is the number of objects. In the bottom is how many you're selecting. It is a very similar formula. You still have n factorial in the top, and you have n minus r factorial in the bottom. But what ends up happening is, like I said, there's less possibilities because the order doesn't matter. So A and B is the same as B and A. So in this case, I have to divide by something else, and that something else I divide by is r factorial. So here, from n objects, we're choosing r of them. So just to show you this fits with the prior example, from 4 people, we were choosing 2 of them for the committee. So the way we would write this is from 4, we're going to choose 2, which in that other format is 4, choose 2 in parentheses. So I get the number of objects in the top, 4 factorial. In the bottom, from the number of objects, I remove how many I'm choosing. And in the bottom, then I also add in the number I'm choosing, which is 2 factorial. So I've got 4 factorial on the top. 4 minus 2 gives me 2 factorial. So I have 2 factorial on the bottom. You can go ahead and simplify this if you want and do 4 times 3 times 2 times 1 and cancel stuff out. But these are small enough numbers. 4 factorial is 24. 2 factorial is 2 times 1, so it's 2. And then 2 factorial again is 2. So really this is 24 divided by 4, which leads me to the same answer of 6. So from the 4 people, choosing 2 of them resulted in 6 possible committees. So we're going to start just choosing or finding a few examples of counting how many ways we can do this, and then we'll go ahead and tie this back to the probability of stuff. So starting out, an ice cream store sells 28 flavors of ice cream. We're going to determine the number of 3 dip sundaes, basically meaning you're going to choose 3 different flavors to make a sundae. So from 28 flavors, I'm going to choose 3 of them, okay? Again, you have a button on your calculators for this. However, I like to go ahead and go through this by hand just to show you that your calculator is working and to get used to those factorials. But our formula is we have the 28 factorial on the top. In the bottom, we have 28 minus 3 factorial, and then 3 factorial. So 28 minus 3 gives me 25. So one thing you'll notice that's going to happen every single time is these two are always going to add up to the total number of objects. So you can sit there and plug 28 factorial in your calculator. However, if I pick off some integers, I should get down to this 25. So if I pick off the 28, I'm left with 27 factorial. But I can pick that off, and I'm left with 26 factorial. Pick that 26 off one more time, and then I get down to 25 factorial, which is fantastic because I have a 25 factorial in the bottom. So those cancel each other out. So what that leaves me with is 28 times 27 times 26. And in the bottom, I have 3 factorial, which is really 3 times 2 times 1. So simplifying these, if I look at 27 divided by 3, that leaves me with a 9. And then I'll do 26 divided by 2, which leaves me with 13. Could also do 28 divided by 2, which leaves you with 4. Doesn't matter which one you divide it into. But then I'm left with 28 times 9 times 13. If I plug that into my calculator, I can make 3,276 different Sundays. So again, the order did not matter here. I jumped right into that combination because if I choose chocolate, vanilla, then strawberry, it's the same as if I selected strawberry, then chocolate, then vanilla. Results in the same sundae. Let's now take it up a little notch, and let's now do a combination of 2 different things. So Matthew has 12 shirts and 6 pants in his closet. He must select 4 shirts and 3 pants to bring on vacation. How many different ways can he do this? So I have 2 different events happening, and I need to find the number of ways they both can occur. Then I'm going to use my counting principle and just go ahead and multiply the 2. So if I look at the number of ways to select the shirt, from 12 shirts, we're going to choose 4 of them. So plugging that into my formula, I have 12 factorial, 12 minus 4 factorial, and then 4 factorial. So this gives me 12 factorial over 8 factorial times 4 factorial. And I think at this point, you hopefully will be a little bit comfortable with this, but you can go ahead and simplify the 12 as 12 times 11 times 10 times 9 times 8 factorial. Cancel those out, or you can plug these factorials in your calculator, and there are 495 ways to select the shirt. Now we're going to do the same thing for the number of ways to select the pants. So from the, 6 pants, we're going to choose 3 of them. Again, order is not significant here. So in that formula, that would be 6 factorial. In the bottom, one way you can also think about this, you put the 3 you're choosing, and then the factorial that goes here, again, has to add up to the number up top. So that will end up being 3 factorial, but again, you subtract those 2 numbers. So 6 factorial on the top, 3 factorial on the bottom, and a second one, and this will give us 20 ways in which we can choose his pants. So we have 495 ways to select the shirts, 60 ways to select the pants. So if I'm doing both of these events, I multiply the 2 to see my total number of ways I can select the clothes to bring on vacation. So the number of ways to select the pants and the shirts is going to be the 495 ways to select the shirts times the 20 ways to select the pants, which gives us 9,900 ways that he can pick his clothes to go on vacation. So a lot of different combinations, okay? So we're gonna try just 2 more examples now utilizing probabilities for this. So we're going to have to figure out, does order matter? Does it not? Or also, am I not even doing a permutation or combination, but just arranging so many things? So we'll start out with this one. A presidential candidate plans to begin her campaign by visiting the capitals in 4 of 39 different states. What's the probability she selects the route of 4 specific capitals? So basically, she's going to go from one capital to the next, to the next, to the next, and she picks that out of however many possibilities there are for her to create a route for these capitals, okay? So the route order is going to matter here. Because if I go from Tallahassee to, say, Trenton, that's different than if I start in Trenton and go to Tallahassee. 2 different routes. So the order matters, which means I'm working with permutations. Okay. So we're basically seeing what's her probability of choosing one specific route for these 4 capitals out of however many routes there possibly are. So let's start by finding the number of routes for 4 capitals of 39. So this would be from 39 capitals, we're going to permute or arrange 4 of them. So plugging that into our formula, that's 39 factorial in the top. And for permutation, I just have the difference of the 2 in the bottom. So you can plug this in your calculator if you want, but 39 over 35 factorial is what that becomes. And then if you do want to simplify this, just to show you off to the side here, let me actually just move this over, make life a little easier. This would be 39 times 38 times 37 times 36 times 35. Then I can stop because that matches with the factorial in the bottom. Canceling those out and then going through and multiplying 39 times 38 times 37 times 36 gives us 1,974,024 ways that we can arrange 4 capitals from 39 different states. So the probability that she selects one specific route is going to be 1 out of that many possibilities. So a very, very, very small probability that she selects one specific route, okay? Let's try one more. When 11 basketball players are about to have a free throw competition, they draw names out of a hat to select their order. What's the probability they shoot free throws in alphabetical order? So if I want to figure out the probability, we'll kind of do this one a little bit different so you can see, of getting the free throws in alphabetical order. Thinking about that in terms of just basic probability, it's the number of ways to be in alphabetical order. Divided by the total number of ways to arrange those players to shoot free throws. And so if you think about that numerator, there is a single way those players are going to be in alphabetical order, one set roster. And then in the bottom, if I'm thinking about all 11 of these basketball players shooting free throws, well, the number of ways I can arrange them is exactly 11 factorial. So my denominator is not a permutation or anything like that. It technically is, because from 11 people you're choosing or permuting 11 of them. But really it just ends up being 11 factorial. So there are 11 factorial ways to arrange 11 players. And so if you plug 11 factorial in your calculator, that would give you a 1 in 39,916,800 chance of them drawing names in alphabetical order. And then you can kind of compare this if you wanted to go back up here. Really what this is the number of ways for one specific root, which is 1, divided by the number of ways to pick or to arrange 4 capitals out of 39. So in that bottom, you have that 39 permute 4, okay? So give your best shot with these. All these problems are going to be very different though, and try to pay attention, okay, is order important or it's not? Do I have multiple events going on so that I need to use this counting property? Or do I have just a single thing going on and I just count the number of ways to get that? Pay attention if you're just calculating the number of ways to do it versus are you being asked about a probability? So all of these are going to make a difference into what you need to find for that problem.